And welcome again. We have another problem, and the problem is a mixed one. In fact, this time we have a capacitor in an external magnetic field. So let's read the statement of the problem. That says the corners of a capacitor are connected by a conducting wire loop. You can see it here, and corners of a capacitor are connected by a conducting wire loop, and a bar magnet is dropped. This one is bar magnet, I can see, and a bar magnet is dropped through the loop as illustrated in the figure. How does the charges of the capacitor plates change in the meantime? So you need an answer, and I'm going to analyze the problem as the magnet approaches. The magnetic flux through the wire loop increases. An EMF is induced as per Faraday's law of electromagnetic induction, and the current in the loop starts to flow, which starts to charge the capacitor because the current is flowing through the loop, so it will start charging the capacitor, and the voltage induced in the wire loop is simply proportional to the change in flux per unit time. That is what is Faraday's Lenz's law. Yeah, phi here is flux. So according to Faraday's law, we can write things like this, because the voltage induced in the wire loop is proportional to the change in flux per unit time. And next we need to consider that when the center of the magnetic rod, that is magnetic needle, or what is, I don't remember what we earlier called it, bar magnet, okay. So I think when the center of this bar magnet passes through the loop, then the flux does not change. At this moment, the EMF induced is 0, and when the magnetic rod or this bar magnet moves away, the magnetic flux decreases through the loop. So the induced voltage is in opposite direction as it was initially. And I'm assuming here for simplicity that the bar magnet moves at a constant speed. Simply planning the solution. So, and if the resistance of the wire loop is negligible, the capacitor is charged and discharged in such a way that its voltage is always the same as the induced voltage. Then the charge Q of the capacitor plate is proportional to the voltage, Q equals CV, and C is not changing, so its charge over time can be described by the graph, and I can draw the rate of change of flux as a function of time simply as like this, and because it was 0, then reached to the maximum and then decreased, and the potential difference induced can be written here as, can be drawn like this, and so will be the charge. So will be the charge because Q is directly proportional to B. So the shapes of Q versus T graph and U versus T graph are going to be the same. So thank you very much for watching. This was not a big